I was asked over the break here a question, and I think, in fact, we all think that it's a good question to answer and actually make a separate clip regarding this specific question. So which method is better? So we just saw another new method for solving systems of equations, the method using Cramer's rule. Note that it works only for n by n systems, right? But that is something that is easy to fix, right? If you're missing a couple of equations and it's not n by n, you can construct them artificially just by duplicating the last equation as many times as you need, and you get an n by n system. So that's not a big issue. And so we have Cramer's rule, and we know substitution from high school, and we have the way of just writing the matrix, the coefficient matrix, and doing the row operations. And we had the method of finding A inverse and multiplying that by B to get X. So we're accumulating several ways of solving systems of equations. And the naive question, which is a very good question, is which is better? I get a system of equations, which method should I use? So the answer is, in this course, the systems that you're going to get are usually maybe 3 by 3 systems. 4 by 4 would be a killer, okay? And you should choose whatever method you feel you're the most comfortable with, and it really doesn't make a big difference, okay? However, once beyond this course, in applications in the real world, you're going to encounter systems where n is very big. Very big could be a 3-digit number or bigger, okay? And obviously you're not going to solve those systems manually, okay? So rather, you're going to give your old buddy computer the task of solving the system, okay? And that's still a very, very good question, which method is better for the computer to use in order to solve a system of plenty equations on which it has to work, okay? And better is translated in this sense into a question about resources. How many calculations does the computer have to do in order to solve the system? Where a calculation, a single division is a calculation, okay? A single multiplication is a calculation, okay? How many steps, how many moves does it have to do in order to solve a system of equations where n equals 20? A 20 by 20 system of equations. And what the computer does is an algorithm, right? It gets an algorithm, a set of fixed, a recipe of fixed steps that it has to perform in order to do the calculation. And there's a big theory, a vast theory of calculating the complexity of the algorithm. How many steps does the computer have to do, expressed as a function of the length of the input, of n, okay? So if n is 20 or 200, does it have to carry out maybe n squared moves, or maybe 3 times n cubed moves, or maybe only log of n moves, okay? And in applications, and we mentioned over the break a few of them, but in fact they're really everywhere in image processing and in encrypting, all kinds of methods of encrypting, and in radiation therapy, and wherever you look you're going to see linear systems and linear methods like this. And there are many people that study complexity of algorithms and try to find even very small improvements that enable an algorithm to work in a shorter amount of moves. Less moves, which translate it into less time required in order to do this. And when n is very big, that could be very significant. Okay, to the extent that something, if the number of moves required is exponential in n, then it may be an algorithm which is completely unfeasible, rather than if it's logarithmic, it could run fast and do the job. Okay, so this is a very good question, and the answer is in terms of algorithms and in terms of complexity of algorithms, and that in itself is a big topic. Okay. and improving these algorithms and finding maybe new algorithms which work even slightly faster can have enormous consequences. In particular, you list a patent before you publish it and you make millions of improving an algorithm just by a bit, because many computers all over the world do these calculations every single minute and every single day, many times. Okay, so I think this was worth the couple of minutes we spent on this. It's very important. In fact, it's a bit disappointing that in this course we don't have time to kind of stretch our hands towards the applications and show how we use these ideas in other subjects. Okay, it would be nice to do some cryptography here, or to do some stuff that is not purely mathematical and see where we use these mathematical ideas, but we don't have that time. I can just say a bit of things in order to maybe intrigue you a bit and get you interested. But you're going to see these in not all, but you're going to see applications as you proceed in your studies, and that's why this course is so basic and so important. Okay, so which method is better? Answer method number 3. Now you're going to ask, which is method number 3? Aha, that's the mystery. Okay, questions? Good? Okay, so that's the end of this one.